Hi, the goal of today's video is to teach you how to use the dual range force sensor in conjunction with the Vernier Logger Pro. And there are some subtleties and there's a lot to learn here, so we'll try and take things one step at a time. And I encourage you to practice each of the component parts to the bigger experiment so that when the whole experiment comes together with the force plate and everything, you're well prepared. What we're working up to is using the force plate, which has 3 dual range force sensors, 1, 2, 3, and a top plate to be able to measure the thrust of rocket motors to measure their performance. But we start with a little simpler as we're coming up the learning curve. So this is a Vernier LabQuest, and what this is it's an electronic interface that you can hold in your hand or that you can also use and control with a computer, which is the way we're going to end up doing it. And it has a number of sensors that can be attached, including the force sensors that we constructed our force plate out of. But just to begin to get the hang of it, let's talk about a simpler sensor that you're probably familiar with, and this is just a thermometer. It's an electronic version of the glass thermometers you may have used in a chemistry lab, or that your parents may have used to take your temperature when you were sick growing up. So essentially it's measuring the ambient temperature of the room right now. I'm not sure if it's coming across on the camera, but it's connected to the Vernier, and it's reading 23.3 degrees Celsius, which is a common room temperature. So let's, without further ado, let's connect it to the computer and start digging into the LabQuest functionality. And what we have here is we have a program running on the computer called Logger Lite. You can download this from the Vernier.com website, which I recommend really as soon as you watch the video, because it has features that you can begin exploring even before you have the hardware in hand. So the LabQuest connects to the computer. This is just a normal USB cable. There's a lot of different connectors on here. The USB cable only fits properly into one of them. One end into the USB cable, the other end into the computer. And usually it automatically detects that you've got a LabQuest out there that you just connected, and that there's a thermometer being worked with it. Doesn't seem to be working now, the automatic detection, so let's go ahead and let's do the old-fashioned favorite, close it out and get back in. So we'll just, we want the Logger Lite. So starting it back up, it does detect the thermometer properly, and it's got like a analog thermometer as well as a graph of the thermometer. And there are different capabilities built in here, and you can think, well, what else can you do with a thermometer? It just sits there and measures temperature. That's not very interesting. So if you hold it in your hands and you touch the end where the actual measurement is, you can see that the temperature's rising a little bit, and it's basically doing what you expect a thermometer to do. But there's some other interesting features that now the Logger Lite in conjunction with it allows us to do, and it allows us to measure things as a function of time. In the same way that a bathroom scale, you step on it and it gives you a static reading of the temperature. That's useful for things that have a constant force like your weight, but that's not really useful for things that have a changing force like a rocket motor or other things that we might be interested in. So let's begin getting our minds around this idea of measuring a quantity that changes as a function of time. And if you just hit the collect button here, you'll see that it graphs the temperature as a function of time, and I held it there for a minute. And now it's cooling back off toward room temperature after originally becoming a little warmer from touching it. So if I grab it again, you'll see that the temperature starts to rise, kind of on the quickly side. Hey, nice to know that the mitochondria are still working and I still have 98.6 Fahrenheit going on. So the temperature starts to rise in response to being touched by my finger. Well, not too long after it, if you sit and think about this for a while, you might say, well, that's interesting and all, but how do we control things that we might want to control in another case? For example, how do we control how long the measurement lasts? Something we want to do. How would we measure things at either a faster sampling rate or a slower sampling rate? We don't even really know what the sample time is right now, or the sample rate. If you look here, you can see 66, 66.5. The sample rate is about 1 measurement every half second, or 2 measurements per second. But suppose we wanted something a little faster or a little slower, or suppose we only wanted it over 50 seconds rather than 200 seconds. To make those adjustments, if we come to the experiment tab, and let's go ahead and I'm going to zoom in. So we've zoomed in the camera onto the computer screen, so hopefully you can see the menu items. So if we go down here to data collection, time-based data collection, that's what we want. And the duration here, suppose we don't want to measure for 180 seconds, suppose we only want to measure for a minute, let's call that 60 seconds. And suppose we didn't want to measure at 2 samples per second, suppose we wanted to measure at 20 samples per second. And we get a little warning note here that says the rate exceeds 2 samples per second, which is the maximum suggested speed for the stainless steel temperature measurements, or the thermometer that we're using. And that's okay, because the force sensor that we're going to be demonstrating later actually goes a lot faster. So let's just get the hang of measuring things at a little faster rate and see how the Logger Light software works. Alright, so click Done, and then when we want to start a new measurement, come back up here to the Start Collection button and Start Collection, and it gives you this, you didn't save what you did last, you really want to erase it, and we can erase it in this case because we don't need to analyze it later. So erase and continue. So now it's clipping along, measuring the temperature 20 times per second. So if we wanted to, as it's doing this, we can go ahead and scroll down, and you can see that the time interval is 0.05 seconds now, and 0.05 is a 20th of a second. And it's accruing new measurements at that rate, and it'll probably keep going at that rate for the number of seconds that we set it to, which I think was 60. And then if I let go, it'll come back down. Alright, so this is interesting, and this is how the temperature sensor works. And it's also how you can set the sample rate for any number of measurements that you might be interested in. Okay, so let's go ahead and let it finish. So it stopped at 60, and let's think about how to save. So we want to save this. If we save as, and it'll give me this complex, all the files in my directory. So why don't we go ahead and let's make a new, we'll make a new folder, and we'll call it Vernier, because Vernier is the name of this, the LabQuest. And we'll save it as practice temps. Alright, and this is actually saving it in a file format, and we've saved it, but it's in a proprietary file format now that only the Logger Light software can read. So if we wanted to bring it up and analyze it, we could do that, but we're kind of restricted to the Logger Light software, and we might want to, for example, import it into a graphing program or a spreadsheet or something else for other kinds of analysis. So you can also, if you export as, you can export it as a text file, and then we could call the text file, let's call it practice temp.text. Well, it's going to append, it's going to put the so then if we go to our directories, and if we let's get to, if we just navigate over to Vernier, and if we open practicetemps.txt, what we see is just a normal text file. You can open it in a word processor or a spreadsheet. Usually with a few simple edits you can import it into most graphing programs, and it is the first column is the time where the measurement was made, and then the second column is the temperature, to way too many significant digits. Alright, so let's go ahead and exit that. So that gives us a good idea just how the Vernier box here works, as well as how the Logger Lite software works. Alright, so before we hook up the, I'm going to zoom out. Alright, before we hook up the force sensor, and we're going to start by looking at one force sensor as we build our skill and get ready to look at three, let's talk a little bit about calibration, because when dealing with these force sensors, there's a lot of talk about calibration and a lot of need to carefully calibrate things and to carefully set the zero. So I want to give a sense of what calibration means, why we bother to do it as scientists, and why it's important to build up to kind of the practical details of how it works. We really have an accuracy goal in most of our experiments of less than 1%. So we don't just want to measure things to say that we measured them, and we also don't want to treat instruments as black boxes. For example, with the thermometer there, do we just believe that this instrument is accurate? How do we know that 23.5 degrees is really exactly 23.5 degrees? How do we know that all the significant figures that are in the data file are accurate? Of course, all the significant figures there aren't accurate. So how accurate is it really? Well, if we wanted to test the accuracy of the temperature probe, what we'd probably do, since we're close to sea level here, and if you're close to sea level, you get some distilled water and you boil it, and you measure the temperature of boiling distilled water, and that is defined to be in the metric system 100 degrees Celsius. Then you could take an ice water mix. Again, you'd use distilled water to really do this accurately. Freeze some distilled water into ice cubes, crush the ice cubes, get about a 50-50 mix of the crushed ice cubes and distilled water, put the temperature probe in the ice water bath, and then if you're really accurate, then your temperature reading should be 0.0 degrees Celsius. And if your temperature reading of your ice water mix isn't exactly 0.0, or in your boiling water isn't exactly 100.0, then you know you have a sense for how inaccurate your thermometer might be. And this is actually how old-fashioned glass thermometers were invented, right? They would take a glass tube, have the bulb at the end with the mercury. They'd submerge it in an ice water bath, and they'd mark that as 0 degrees Celsius. Then they'd put it in boiling water, and they'd mark that as 100 degrees Celsius. And they'd make, the tick exactly in the middle would be 50 degrees Celsius. And then if you make 100 evenly spaced tick marks along the way, you've essentially calibrated that thermometer to 1 degree Celsius. So that's the general idea of what we're trying to do anytime we're talking about calibration. Is you want a known good zero, you want a known good point with a known quantity, whatever quantity it is that you're measuring, and then you develop a linear scale in between. And there are a lot of tests, a little bit beyond the scope of what we're doing here, about whether or not a linear scale is very good. You can kind of take our word for it here with the force sensors that you can get to better than 1% accuracy with the force sensors and the force measurements if you use a linear scale, as long as you try and keep in mind that when you're calibrating it, the full scale that you're calibrating to is close to the actual force that you're trying to measure. For example, if you're measuring rockets with a peak force or peak thrust of 10 to 20 newtons, you want your calibration to ultimately be somewhere between 10 and 20 newtons.